Hello and welcome to Instant Genius, a bite-sized masterclass in podcast form. Every Monday and Friday you'll hear world-leading scientists and experts talking about the most fascinating ideas in science and technology today. I'm Jason Goodyer, Commissioning Editor at BBC Science Focus. In today's episode, we're lucky enough to be joined by Prof Jim Al-Khalili, a theoretical physicist based at the University of Surrey, author of several best-selling books, and the long-time presenter of BBC Radio 4's The Life Scientific. Jim, thank you so much for joining us.
My pleasure. Glad to be here.
So today we're going to delve into the mysterious world of quantum mechanics. So these days, the word quantum is sort of thrown around a lot for washing powders, running shoes, and all sorts.
I have quantum deodorant.
Exactly, yeah. It seems to be everywhere. So
yes.
First off, what does it actually mean?
Well, quantum goes back long before the quantum mechanics came on the scene. The quantum is the smallest discrete jump you can have. The origin in physics goes back to Max Planck, who in 1900 suggested that warm bodies radiate energy not as a continuous flow, but in discrete chunks. There are the smallest indivisible chunks of energy, which he called quanta. And from then, that kicked off the quantum revolution and led a couple of decades later to the fully blown quantum mechanics.
So let's have a look at quantum mechanics then versus classical mechanics or Newtonian mechanics. So first off, there's the Schrödinger equation that people might have heard of that sort of describes the strange property in quantum mechanics of waves behaving like particles and particles like waves. So what can we say about that?
Well, we are celebrating the centenary this year of quantum mechanics and indeed of Erwin Schrödinger coming up with his famous equation. It's fair to say that this is back in the mid-1920s. There was a lot of confusion about what it means to say that particles behave like waves and waves behave like particles. And physicists were arguing amongst themselves as to, who had the correct way of explaining what was going on down at this microscopic level. Schrödinger's equation is a wave equation in the sense that it describes the behavior of waves. He believed that electrons trapped within atoms don't orbit around as particles along specific trajectories, but are as spread out waves. So he really was of the view that there weren't particles, they were all waves.
Right.
And of course, there were other views. Werner Heisenberg, who also developed a version of quantum mechanics that same year, 1925, hated the idea that you could describe atoms, electrons, as physical things. He said, no, they're abstract quantities. We can't really say what they look like, what they are. We can describe them mathematically and we can predict the results of experiments, but they're not real physical waves, which is what Schrödinger believed.
So we've carried out some really strange experiments investigating this phenomena. I think probably the most famous one is the double-slit experiment. So could you explain that?
Yes, some years back, I gave a talk at the Royal Institution in London about this subject, weirdness of quantum mechanics. And I came to explain the two-slit experiment in all its weirdness. And at the end, I made the mistake of saying, if anyone has a logical, common sense way of explaining what's happening here, give me a shout because, the King of Sweden might want to call you up and offer you a Nobel Prize. So, of course, I forgot that I wasn't just talking to the few hundred people in the audience there, but the Royal Institution record their lectures and they go online. To this day, more than 10 years later, I probably get one or two emails a week saying something like, I don't have a background in physics. However, I think I've figured out what's going wrong in the two-slit experiment. To the extent that even on my website, I've said, look, if it's two-slit experiment explanations, please don't email me. But long story short, the idea is if you fire a subatomic particle at a screen with two slits, and then there's another screen behind it that would capture the arrival of that particle, then you would imagine if they behave according to Newtonian mechanics, that particle, if it gets through the middle screen with the slits, it'll either go through the upper slit or the lower slit, and you'll get an accumulation of particles on the back screen adjacent to the two slits, two sort of piles of particles. But we know if you send light through, this goes all the way back to the beginning of the 19th century, Thomas Young explaining the wave nature of light, saying that light travels as a wave, and so it passes through both slits simultaneously, and then the other side of each slit acts as a new source of light, and the two waves interfere and interact. You get an interference pattern. If quantum particles behave like waves, then they should also give an interference pattern. And indeed they do. And we've tried to understand how this is. You could even send a particle, say an electron, one at a time at the screen with the two slits. You'd think that it would either go through one slit or the other. But after many, many electrons pass through, and by the way, on the back screen, it hits as a dot of light. The back screen can be a fluorescent screen that shows a flash of light when an electron arrives. So you see it arriving as a particle. But somehow, as it goes through the two slits, you don't see individual electrons, whether they go through one or the other, but cumulatively they build up an interference pattern. And if you try and catch the electron out to see which slit it goes through, it knows you're watching and behaves like a particle. It's only when you look away that it behaves like a wave. So, I mean, the physicist Richard Feynman said the two-slit experiment is the central mystery of quantum mechanics. If we could understand that logically, we do understand it, but you don't entirely get rid of the weirdness.
So another weird aspect of quantum mechanics is superposition. So what do we mean by that, and how does that work?
Well, the idea, I mean, again, this is a property of waves. When you have two waves interfering, we can talk about them as superposing on top of each other. In the two-slit experiment, the waves coming from each slit will superpose on the other, and so where you get a crest and a trough, they'll cancel out. Two crests will magnify the amplitude. In quantum mechanics, quantum objects, particles, waves, whatever you might call them, like electrons or protons or neutrons, they have this property that of superposition, in that you can talk about them as not being in one place or having a particular energy or momentum, but rather a combination of being in lots of places at once, or having lots of energies at once. So we say they are in a superposition of different states. And only when you measure them, for example, measure what energy they have, do you kill off that superposition and you select just one outcome. Same with position. It could be in a superposition of different places. Only when you get a detector to locate the position of the electron do you see it somewhere else, and that kills it. That's what is often called collapse of the wave function, killing off the superposition. Again, it's a property of waves, which is not so strange, but when it comes to subatomic particles in the quantum world, it seems weird.
Yeah, so you mentioned there measurements. There's a fundamental problem in quantum mechanics that was with measurement that was discovered by Heisenberg.
The idea of measurement brings in the role of the observer. And that's led to a lot of confusion among students of quantum mechanics and the wider public when they learn about the theory. When a quantum object or system, let's say an electron, is in a superposition of different states, say an electron that can be in a superposition of different energies at the same time. It doesn't have a precise energy. It can have a probability of being in different energies at the same time. When you measure it, you pick out just one. How does that happen? Schrödinger himself actually was very unhappy with the idea, and he developed his famous paradox, Schrödinger's cat. Put the cat in the box, and you close the box, and in with the cat is a radioactive material that can emit a particle that can release poison that can kill the cat. But until you open the box and measure, the cat, because it's also made of atoms, is in a superposition of being dead and alive at the same time. Today, we know how to resolve the measurement problem to a large extent, something called decoherence. A quantum system isn't alone, it interacts with its surroundings. But there's still an issue as to what happens to all the other possibilities that you don't see when you measure. If it had several energies or was in several positions at once, and you measure it, you find it in one. It's not like you've got something closed in a box and you don't know what it is, or you put you have two boxes, one with a left glove and one with a right glove, and until you open the box, you don't know which one's left and which one's right. So of course, you open the box and you see a left glove, you immediately know the other one is a right hand. So it's not just our ignorance that leads to these probabilities in quantum mechanics. They really are having all possibilities at once. And this leads to issues in philosophy about how to interpret what's going on. one of the most logical ways, although also weird, is the idea that all possibilities happen. When we measure something, open the box to see the cat is alive. There is another parallel reality in which we opened the box and found the cat is dead. That solves the measurement problem, but it means you have to buy into this idea that there are multiple realities. This is called the many worlds interpretation.
Yeah. So you mentioned there the glove analogy. So that's a bit like quantum entanglement. So can you tell us about that?
So quantum entanglement, we are coming to realize, is one of the most fundamental aspects of quantum mechanics. Very often, even students at university studying physics don't get taught about quantum entanglement. It was deemed as rather extreme weirdness of quantum mechanics. Even Einstein didn't like entanglement. But we're realizing it's quite fundamental. The basic idea is that you have two particles. Now, a single particle can be in a superposition of two states. Let's say an electron can be spinning in two different ways. We call it spin up and spin down. The rough classical analogy is to say it's spinning clockwise and anti-clockwise. If it's in a superposition, it's doing both at the same time. Don't even try to figure out what this means, but for a particle to spin clockwise and anti-clockwise at the same time just doesn't make sense at all. But that's what a quantum superposition would mean. Now, if that particle has interacted with that electron with another electron, then the fate of the second one becomes intertwined with the first. So if the first one is in a superposition of spinning both ways at once, the second one's also spinning both ways at once. And measuring one will instantaneously change the state of the other one. So we talk about those two electrons as being quantum entangled. And they would hold this quantum entanglement provided they're not disturbed and the entanglement destroyed, however far apart you separate them.
And this has been tested.
Absolutely. I mean, this is something it's well established now. I mean, maybe weird. Einstein may not have liked it, but it's one of the fundamental features of modern technologies in the quantum world that we're developing at the moment. Quantum computing, quantum encryption, and so on. They all rely on this idea of quantum entanglement.
So not just with like us humans understanding physics and trying to figure it out, it also happens in the animal kingdom. So something called quantum biology. So I've heard that some birds use quantum mechanics in order to navigate when they're migrating.
So we think. I mean, I should say quite clearly that we don't yet have the experimental confirmation that this is what happens, but it does seem to be the case. This is the only theory in town that explains what happens. So I should say, first of all, quantum biology is basically the idea that life has evolved the ability to make use of the quantum world in a way that inanimate matter doesn't do. So it's not saying we are made of atoms and atoms behave quantum mechanically, then of course quantum mechanics plays a role in life. That goes without saying. No, some of these ideas like quantum entanglement, they might play a role in life. It was known since the 1970s that certain animals, birds, marine mammals and so on, can sense the Earth's magnetic field. And even that in itself is weird. You know, how can something as weak as the Earth's magnetic field affect an organism's chemistry? It's one thing sticking you into an MRI scanner. That's a very powerful magnetic field, but the Earth's magnetic field is very weak. But these animals seem to have evolved a chemical compass of some form. And at the moment, the current theory suggests that, well, first of all, we believe this compass is based somewhere in the animal's retina. So the European robin is the classic example that uses magnetoreception. As it's flying, light enters the retina, it hits one of a pair of entangled electrons. So they're both two electrons sitting on one atom. They're entangled in the sense that one is spinning one way, the other one has to be spinning in the opposite direction. The photon comes in, knocks an electron off the atom. They're now still sitting within this protein called cryptochrome, but they're not on the same atom anymore. They're quantum entangled. That means their spins are still correlated. They're still interconnected in some way. And the way these two electrons spin is very sensitive to the orientation of the bird in the Earth's magnetic field. And so the Earth's magnetic field can be sensed by the bird through these entangled electrons, that sort of cascades a signal through to the bird's brain that tells it what direction to fly. So quantum entanglement might help the European robin migrate every autumn down to the Mediterranean from Scandinavia. It's a lovely idea. The robin uses a theory that even Einstein didn't like because it was so wacky. That doesn't make it right, doesn't make it, the correct answer to how the birds navigate. But we don't have yet another explanation for this magnetoreception in animals.
So you often hear quantum mechanics called the sort of physics or the science of the very small. So what is the sort of scale limit? And, are we pushing further and further against that in experiments?
There is still to this day a very vibrant area of research that examines the boundary between the quantum world and our everyday macroscopic world, what we call the classical world, classical mechanics compared with quantum mechanics. It's a very vague, broad area, and it depends on what experiment we're doing. It depends on how careful we're examining a particular system. Certainly, you get down to the level of atoms and molecules. You're in the quantum domain. You should not expect them to behave classically, and certainly in our everyday world of tables and chairs and balls and humans and so on, you don't see quantum behavior unless you dig down into the atomic structure. But in between, it's difficult to know. So we're, for example, developing quantum sensors, quantum computers. These are objects that we can, use to carry out certain tasks, and they rely on ideas like quantum entanglement, but they're large systems. Of course, the bigger a system gets, the harder it is to retain the quantumness. The quantum effects are very delicate, very sensitive to the surrounding environment. So the more complicated a system is, the less likely it is that we're going to be able to maintain any quantum behavior for very long.
On the sort of other side of the coin, then, is the science of the very big, the physics of the very big, which is Einstein's theory of relativity. And quantum mechanics and relativity don't get on, do they?
They don't like each other.
So
no.
why is that? And, what will we ever be able to get them to agree?
The hope is that we will, and many physicists are working in this area of quantum gravity. But mathematically, the mathematics of quantum mechanics is very different from the mathematics of the very large, Einstein's general theory of relativity. General relativity is all about fields and geometry and the curvature of space-time, whereas quantum mechanics is all about the discreteness of particles and probabilities and so on. And mathematically, the theories don't mesh together. But we sort of know they have to. There are certain environments or situations where we need both quantum mechanics and general relativity to understand them. For example, the nature of the Big Bang, the birth of the universe. The Big Bang was predicted by general relativity and later confirmed that is really how our universe was born by lots of experimental evidence. But we can't explain that very moment, the initial, what's called the singularity, the beginning of time, where time and space and matter all first appeared, without quantum mechanics, because quantum mechanics also describes the very small, and the universe was very small at the Big Bang. So we feel we need a theory of quantum gravity. Sometimes people talk about this as a theory of everything, not everything as in including psychology and sociology, but everything within physics. But we're no nearer, I think, than we were 4-5 decades ago. Stephen Hawking famously wrote an article back in the early 80s saying we're almost at the end of theoretical physics. We've almost got to our theory of everything, just dot some I's and cross some T's. Back then, the idea was there were ideas like superstring theory was just emerging on the scene. Supergravity was another idea. People have been working on string theory now for decades. There are other ideas, rival theories, that could become the theory of quantum gravity. There's something called loop quantum gravity.
Yeah.
But we don't know which of them is the correct one, if any of them are indeed the correct ones. And it's frustrating. Because we thought we were getting close, and they all have their problems. String theory is probably the one that's most popular in the sense that most physicists, theoretical physicists, are working in. And slow advances are being made. It turns out it's a very powerful mathematical construct that might even be very useful and might even help us answer other questions in other areas of physics. But we don't yet know whether it's the correct theory of quantum gravity. Is it the one that's going to finally bring quantum mechanics and general relativity together? It's frustrating. And of course, one of the problems is we don't yet have a way of experimentally testing some of these ideas. So many physicists will say, well, that's not even real science then. Physics is an empirical discipline. And as you can test your theories, they might as well be, theology rather than proper science. So it can be frustrating. I don't quite subscribe to that, but I do think that, we are a long way yet from finding a way of merging quantum mechanics with relativity.
Great. So thanks very much for joining us. Been a pleasure speaking to you.
My pleasure.
Thank you for watching this episode of Instant Genius, brought to you from the team behind BBC Science Focus. That was Professor Jim Al-Khalili. If you liked what you just saw, then please do consider liking and subscribing to this channel. Also, why not check out the audio-only version of Instant Genius podcast that's available on all podcast platforms. Every Monday and Friday, we speak to some of the biggest names in science and technology to talk about the most fascinating ideas around. The current issue of BBC Science Focus magazine is out now. Pick up a copy wherever you buy your favourite magazines or download us on your app store of choice. You can also find us on Apple News or online at sciencefocus.com.